In this video, we're going to talk about the partial fraction decomposition of a rational function with real coefficients. So the idea is that if you have a function that's a polynomial divided by another polynomial, you can write it as a sum of other rational functions. So a rational function is a polynomial over a polynomial. And let me give an idea of how it works. So for instance, if you have 1/2 plus 1/3, this is equal to, this is equal to 3/6 plus 2/6, which is 5/6. And partial fractions is about, if you have 5/6, how can I write it as something over 2 plus something over 3? So if I have constants a and b, and 5/6 is a over 2 plus b over 3, how am I going to figure out what a and b are? And if you cross multiply, you're going to get 5 equals 3a plus 2b, right? And you can see that if a and b are 1, then it works. Then 3a plus 2b does equal 5, so you can make a and b equal to 1. Now you could also make a and b different, so you can make a like 10. If you made a equal to 10, then you can get 5 equals 30 plus 2b, and then b is negative 25 over 2. Okay, but the easiest one is if a is 1 and b is 1. So partial fractions for rational functions is basically about how to do that for a polynomial over a polynomial instead of just a number divided by a number. So the general setup is, suppose that you have a rational function, so you have a polynomial, say p of s over q of s, where the degree of p of s is less than or equal to the degree of q of s. So suppose you have the setup, then q of s is always going to be able to be factored in the form s minus r1 to s minus r, say k. So these are the distinct, the linear factors. Now you might have powers of s minus r1 or s minus r2 or whatever. So it might be, raised to the e1 power, and then s minus rk raised to the ek power. And then you might have something, and let's say that the coefficient, the leading coefficient of q of s is 1. So you don't have something like 2s squared for q. It's just like s squared plus 2s plus 5 or something like that. So you can, whenever you have a polynomial where the leading coefficient of q of s is 1, and these are with real coefficients, then you can factor q of s by factoring out all the possible linear terms, and then what you're going to get, you can factor as quadratic terms. So they're going to be like s squared plus b1s plus c1, say to the, f1 dot 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 s squared plus b, I don't know if there are like n of them, b sub ns plus cn to the f sub n. So that's the general form of how you can factor a polynomial with real coefficients as much as possible. So if you have q of s like this, then you can always write P of S over Q of S as some constant over, so I'm looking at this S minus R1 to the E1 term. This S minus R1 to the E1 term, you get a term that's A over S minus R1, so A is a constant, so let's call this A1, plus A2 over S minus R1 squared all the way to the E1. So you have S minus R1 to the E1 here, and then A, so you have E1, E sub 1 like this, okay? And then you do the same thing for all of the S minus Ri's. So you go up to S minus Rk to the Ek, and you're going to get something so similar for all S minus Ri to the Ei. Okay. And then for these quadratic terms, so you have this, you're going to get something similar where you go a degree down. So you're going to get something like B1S plus C1 over S squared plus B1S plus C plus like B2S plus C2 over S squared plus B2S plus C2. Oh, oops, these are the same. Okay. S squared plus B1S plus C1 squared plus dot 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 all the way to, so if the power is F1, then you have F1 of these. So it's B like F1S plus C sub F1 over S squared plus B1S plus C1 to the F1. And then you keep going, so it's similar for all of the S squared plus BIS plus CI to the FI. So that's the general way to decompose. This is the partial fractions decomposition. Now I know it looks very complicated, but I'm saying the general fact, and we'll do examples that are much simpler than this. But this is the general form for how to write a polynomial, how you can express a polynomial over another polynomial if the degree of the numerator is less than the degree of the denominator. So I just wanted to get the general form out there so that you know what the general form is. Now let's take a look at some concrete examples. So, example, let's say you had 7s minus 1 all over s plus 1 squared times s plus 2 times s minus 3. So first of all, the degree of the denominator is 4 because you have this s squared times s times s. So you're going to get an s to the 4th. And that's the biggest power you're going to get. And then the numerator has degree 1 because 7s to the 1. Right? And so you do have a scenario where you can apply partial fractions because the degree of the numerator is less than the degree of the denominator. So if you have something like, oh, let's not do s plus 1 squared. Let's just do s plus 1. That's actually, yeah, let's do it like this. Like that. Okay. S plus 1 times s plus 2 times s minus 3. So if you look at the theorem, right, you have this part, this linear part, s minus r1 times s minus r2 times s minus r3, and your exponents are all 1 because you don't have like s plus 1 squared on the bottom or s plus 2 squared. It's just 3 different linear factors, s plus 1, s plus 2, and s minus 3. So the theorem says, okay, what does the theorem, where's the theorem? It says, so your E1, E2, and E3 are all 1. And so what you're going to get is you're just going to get this A1 over S minus R1. You don't have an S minus R1 squared. And you're going to get an A2 over S minus R2 and an A3 over S minus R3. Okay. So you can write this as A over S plus 1 plus B over S plus 2 plus C over S minus 3. Notice that the degree of the numerator is always 1 less than the degree of the denominator. So for the linear terms, which is what we don't have any quadratic factors. We just have linear factors, they're degree 1, and then the constants have degree 0. And similarly, when you look at the general form here, when you have a quadratic, and we're going to see examples of this, when you have a quadratic, the degree of the numerator is going to be degree 1. It's a linear term. Okay. So the question is, how do you find? So the theorem says that there are constants A, B, and C that make this inequality, this equality true. The question is, how do you find A, B, and C? Well, first, we're going to have to do some algebra. So let's multiply the denominator on both sides. So multiply both sides by Q of S. Just to be clear, that's Q of S, that's our P of S. So you multiply both sides by Q of S, what are you going to get? You're going to get 7S minus 1 equals. So now what are you going to get when you multiply the right-hand side by the denominator? So when you look at A over S plus 1, what's going to happen is the S plus 1s are going to cancel, and that's it. So you're going to get A times S plus 2 times S minus 3. And then similarly for the B term, you have B over S plus 2. When you multiply by Q of S, the S plus 2 factors are going to cancel. So you're going to get B times S plus 1 times S minus 3. And then you're going to have the C term, C over S minus 3. And when you multiply that by Q of S, the S minus 3 terms are going to cancel. So you're going to get C times S plus 1 times S plus 2. Now the question is, what are A, B, and C? Now, do you agree that if you can find A, B, and C that will make this true, this equality without the fractions, right? There's no fractions anymore. If you are able to find A, B, and C that make this true, then you can divide both sides by Q of S and then get the equality with the fractions. So we want to find A, B, and C that make this equality true. And there are a couple ways to do this. So let's put a star because I'm going to refer to this equation. Okay. And then I'm going to show you 2 ways of doing this. So one way is to equate the coefficients of the various powers together. Because if you have 2 polynomials that are equal, the coefficients of the degrees have to be equal. So if you look at the right-hand side, okay, if you distribute the whole thing, and I'm going to skip this step, but just imagine multiplying this out, multiplying that out, multiplying that out, and then combining the like terms, which at this point I'm assuming you know how to do, so I'm not going to go over how to do it. So if you do it, you're going to get A plus B plus C times S squared plus negative A minus 2B plus 3C S plus negative 6A minus 3B plus 2C. Okay, that's what you're going to get when you simplify the right-hand side, and then that is equal to 7s minus 1. Okay, and that's 0s squared plus 7s minus 1. So now you have something where you have s squared terms, right? You have s terms, s here, and you have a constant term. This constant and that constant. And this is a 7s plus negative 1, so the constant's negative 1. Well, you have these two polynomials, they're equal for all s. So it's, you're not saying that these two polynomials like intersect, right? It's not like, when you have a parabola and a line and they meet, they're the same parabola, right? They're the same whatever polynomial. So when you have that, the coefficients have to match. So in this case, the coefficient of s squared on the left is a plus b plus c. The coefficient of s squared on the left, did I say that? The coefficient of s squared on the right is a plus b plus c. The coefficient of s squared on the left is 0. They're the same, so what do we get? We get that a plus b plus c is equal to 0. Similarly, let's match the coefficients of s. On the left, you have the coefficient of s is 7. What's the coefficient of s on the right? Negative a minus 2b plus 3c. So they're the same. Let's write that down. Negative a minus 2b plus 3c is equal to 7. And finally, we have to set the constant terms equal to each other. And on the right, you have this. What's the constant on the left? Negative 1, because remember, it's 7s plus negative 1. So what equation do we get? Negative 6a minus, that's a 3. Minus 3b plus 2c is equal to negative 1. So now we have these three equations. What can we do to solve for a, b, and c? Well, we use our algebra facts about how to solve a system of linear equations. And when you solve a system of linear equations, and if you know how to do matrix algebra, you can even just write this as a matrix and then do some matrix algebra, or you can just solve it. Well, you solve it however you want. And when you solve it, so you solve, and I'm not going to write out the steps of solving this because I'm assuming that we know how to do this and I want to focus on the big picture. When you solve it, you get a is equal to 2, b is equal to negative 3, c is equal to 1. Well, those are our constants. So therefore, we're done. 7s minus 1 over whatever q of s was, s plus 1 times s plus 2 times s minus 3 is equal to, okay, let's look back. It was a over s plus 1 plus b over s plus 2 plus c over s minus 3. And now we know what a, b, and c are. So it's going to be 2 over s plus 1 plus negative 3. So I'm going to write as minus 3 over s plus 2 and then plus 1 over s minus 3. And that's how you do it. That's the partial fraction decomposition of this rational function. Okay. Now I'm going to show another way. Well, the other way is, it's after you multiply both sides by q of s. So the first way we did it, just to summarize, is you distribute the entire right-hand side and you set the coefficients equal to each other. And when you set the coefficients equal to each other, you get a system of equations, and then you solve the system of equations. There you go. You get the answer. Another way of doing it is a little simpler. So another way. But it's worth seeing both ways, because if you have a particularly simple example, this first way is actually probably a little bit easier. Anyway, the other way is, so we have this, This is what we're working with, and we're trying to find A, B, and C. Well, we're trying to find A, B, and C that will make this true no matter what S is. So you could say, oh, well, this has to be true when S is 1, it has to be true when S is 2, it has to be true when S is 3, when S is pi, when S is whatever number you want, negative a trillion times the square root of 7. It also has to be true for that S. If you can make that happen, right, no matter what S is, then you'll be able to divide both sides by Q of S and then get the equality that you really want. Because the equality that you really want, the original one is this. Right? That's the one that you really want. But if you can get the blue thing to be true, this equality without the fractions, then you can just divide both sides by Q of S and then get the green equality, which is what you really want. So how can we figure out what A, B, and C will make the blue equality true for all S? Well, the idea is to plug in specific values of S that will allow you to solve for A, B, and C. So can you see a value of S, okay, so that when you plug it in, the right-hand side simplifies a lot? There are a few values. You can plug in negative 2. What happens if you plug in negative 2? Do you see what's going to happen if you plug in S equals negative 2? This term, what's that going to turn into? It's going to turn into 0 because of this S plus 2. This S plus 2, if S is negative 2, then S plus 2 is equal to 0. So that whole thing is going to be 0. And similarly, this whole term is going to be 0 because there's an S plus 2. And then you're going to get something in the middle, and then you're going to get that number on the left, and then you can set them equal and solve. Okay, let's see what happens if you plug in S. So the idea is to choose values of S in that start equation, ideally to create zeros. So for instance, if we plug in S equals negative 1, on the left you're going to get 7 times negative 1 minus 1. And on the right, I'm just going to write it all out. Oh, I'm plugging in negative 1. Why am I plugging in negative 1? Because if you plug in negative 1, the B term, this term will be 0, and the C term will be 0. So if you plug in negative 1, you're going to get 7 times negative 1 minus 1 equals A times negative 1 plus 2 times negative 1 plus 3 plus, and I'm just writing it all out just to show you, B times, and when you plug in negative 1, you get 0. So you're going to get B times 0 times 0 minus 3 is negative 3. So B times 0 times negative 3, and then C times 0 times 1, right? Because negative 1 plus 2 is 1. So you're going to get this. Well, this thing, that thing is equal to 0. This thing is also equal to 0. So what you end up getting is, on the left, you get negative 8. And on the right, you're going to get A times 1 times 2. So you get 2A. Did I do that right? Oh, is it a minus 3? Yeah, it's a minus 3. Okay, this should be a minus. So you're going to get negative 4A. So you divide both sides by negative 4, you get A is equal to 2. See, so we found A is equal to 2. Okay. And then, what can we do to get B? Well, if you plug in negative 2, the A and C terms are going to become 0. So let's plug in negative 2. That's going to give you 7 times negative 2 minus 1 equals b times negative 2 plus 1 times negative 2 minus 3. And that's going to be negative 15 equals 5b. So you divide both sides by 5, you get b is equal to negative 3. So now we have a and b, and we just need to find c. Now what can we do to figure out c? What's a good value of s to plug in? A good value of s to plug in is going to be 3. Because if you plug in 3, you see this s minus 3 in the a and b parts. So those are going to turn into 0. So let's plug in s equals 3. If you do that, you get 7 times 3 minus 1 equals c times 4 times 5. And that's going to give you 20 equals 20a, 20 equals 20c, so c is equal to 1. And so we get the same as before. A is 2, b is negative 3, and c is 1. So you're going to get 7s minus 1 over s plus 1 times s plus 2 times s minus 3 is equal to 2 over s plus 1 minus 3 over s plus 2 plus 1 over s minus 3. Right? Same as what we got before. So that's another way of doing it. And that's what you get when you have distinct linear factors. So this was the easiest case when you have distinct linear factors. Let's see what happens when you also have linear factors, but you have powers that are, bigger than 1. So if you have repeated linear factors, well, we're going to refer back to the formula that I had above, because that formula works no matter what your scenario is. So here's an example, s squared plus 9s plus 2 over s minus 1 squared times s plus 3. First we have to make sure that we get the form right, that we know what the form is before we start solving for the coefficients. And when you look here, we have a repeated linear factor. Okay, let's go back to the formula, which is this. I'm gonna maybe put like a star or something, just to indicate that that's what we're looking at. So our Q of S, our denominator, is s minus 1 in parentheses squared times s plus 3. So in this case, you're going to get, the s minus 1 is going to go out to s minus 1 in parentheses squared. Other than that, it's pretty much the same. So for this s minus 1 part, you're going to have a sum of two things. There's a constant over s minus r1 plus a constant over s minus r1 squared. So what does that look like? Here, we are going to get a constant over s minus 1 plus a constant over s minus 1 squared. That takes care of the s minus 1 squared. And then there's the s plus 3 part, and we're going to get a constant over s plus 3. That's the form that we have. And now we're going to solve for a, b, and c. And you pretty much do the same thing. It's slightly more complicated when you have a repeated linear factor, and we'll see what happens. So again, we're going to multiply both sides by the bottom, and you're going to get s squared plus 9s plus 2 equals, well, it's a good idea for you to write down what we're going to get and then check. Okay, so if you want, you can pause the video and then write down what you're going to get and then check. Okay, let's see what you get. So when you multiply both sides by the bottom, this a over s minus 1, okay, there's an s minus 1 squared that you're multiplying by. So what's going to happen is one of the s minus 1 factors is going to cancel with an s minus 1 on the bottom, and you're going to be left with an s minus 1. So you're going to get a times s minus 1, and then you still have the s plus 3. So you get that. And then for b, the s minus 1 squared is on the bottom, and so that's going to cancel with s minus 1 squared, and so you're going to get b times s plus 3. And then for c, the s plus 3's cancel, so you get c times s minus 1 squared. Okay. Well, here you could, again, do the thing where you distribute the entire right-hand side and set the coefficients equal to each other with the coefficient on the left. Right? So you multiply all of it out, you get something s squared plus something s plus something, and then you match those with the coefficients on the left. But we're going to plug in values because it's easier. So what are the two values that we're going to plug in for s that will make things as easy as possible? 1 and negative 3, because that's going to give us 0, just like before. So let's plug in s equals 1. When you plug in s equals 1, you're going to get 1 squared. I think it's a good idea to write out what you get. So 1 squared plus 9 times 1 plus 2 equals, and then you're going to get 0 for the first term, and then b times s plus 3 is 4, so 4b, and then the c term is going to be 0, so 4b. And then you're going to get 1 plus 9 plus 2 is 12, so 12 equals 4b, and what's b equal to? 3. Now let's plug in s equals negative 3. You're going to get negative 3 squared plus 9 times negative 3 plus 2 is equal to 0 plus 0 plus c times negative 4 in parentheses squared. So that's 16c. Well, the left-hand side is going to be 9 minus 27 plus 2, which is negative 16. So negative 16 equals 16c. C is negative 1. So we have b and c, we just need to figure out a. Now, at this point, we plugged in all the values of s that will give you a bunch of zeros, right? Because we don't have any other linear factors. So how are we going to solve for a? Well, it's not that complicated. One way to do it is, since we already know what b and c are, we can find one equation. So we can set one of the coefficients equal to each other instead of all three of the coefficients equal to each other. So there are two ways to find a. Okay. One way is to set one of the coefficients equal to each other. And so, for instance, we can check the coefficient of s squared. Well, the coefficient of s squared on the left is 1. So we know that the coefficient of s squared on the right has to be 1. What is the coefficient of s squared on the right? Well, you don't actually have to distribute the whole thing to figure that out. Because what's going to happen when you have this s minus 1 times s plus 3? You're going to get s squared plus something. Right? Something s plus some constant. So this term, okay, that term, when you distribute it out, is going to be as squared plus something s plus some constant. But you know that the constant in front of the s squared is going to be a. And what happens if you look at this? B times s plus 3. Well, that's going to give you bs plus 3b. So there's no s squared term. What happens if you do this? The c times s minus 1 squared. Well, the s minus 1 squared, that's going to give you s squared plus something, plus lower degree terms. And then when you multiply by the c, you're going to get cs squared plus something. Something s plus a constant. You're not going to get any other s squared terms. So when you distribute this out, if you imagine distributing this whole thing out, you're going to get an as squared, and you're going to get a cs squared, and that's it. You're not going to get any other s squareds out of the multiplication. So what's going to be the coefficient of s squared? It's going to be a plus c, because you can add the as squared and cs squared. So you're going to get a plus c in parentheses times s squared, and that's going to be 1s squared. Okay? So you're going to get 1 equals a plus c. And c was negative 1, so 1 is a minus 1, and so 2 is a. So that's a. A is 2. Now you have to be a bit, comfortable with doing this, because you're not actually doing out the entire algebra. You're thinking about what would happen if you just looked at the coefficient of s squared and see what you get. In general, you want to look at the highest degree one, because if you look at the coefficient of s, it'll be harder to figure out what the coefficient of s is going to be. It's easier to look at the coefficient of s squared, and we're going to get a plus c. Okay. So that's one way to do it. Another way is to just plug in another value of s. And often that value of s is going to be 0. So if you plug in s equals 0, into this equation, you are going to get, and we already know what b and c are. So if you plug all of that in, you're going to get 2 is equal to negative 3a plus 9 minus 1. And 2 is equal to negative 3a plus 8. And so when you subtract 8, it's negative 6 equals negative 3a, and a is equal to 2. So that's another way to figure out what a is. Either way, you get that s squared plus 9s plus 2 over s minus 1 squared times s plus 3 is equal to 2 over s minus 1 plus 3 over s minus 1 squared minus 1 over s plus 3. That's the partial fraction decomposition. Okay, so that's what you do when you have repeated linear factors. Now let's look at an example where you have a quadratic factor. So, for instance, let's say you had 2s squared plus 10s over s squared minus 2s plus 5 times s plus 1. So we have to get the form right first before we continue. So we have an s plus 1, a linear factor here on the bottom, so it's just going to be a over s plus 1. And then you have an s squared minus 2s plus 5, and that's not raised to any power, right? So you're just going to get like a bs plus c here over s squared minus 2s plus 5. So it's again, it's a degree lower. So you have a linear factor, a linear term in the numerator above the quadratic polynomial. Okay, so again, we multiply both sides by the denominator. 2s squared plus 10s equals a times s squared minus 2s plus 5 plus bs plus c times s plus 1. Well, let's do the method where you plug stuff in. So if you plug in, what are we going to plug in? You look at the linear factors. Okay. There's an s plus 1 here. So if you plug in s equals negative 1, you're going to get 2 minus 10 is negative 8 equals, okay, a times 1 plus 2 plus 5 is 8. So that's going to give you a is negative 1. Right? You're going to get 0, you're going to get 8a plus 0. So a is negative 1. Okay? Now we still have to figure out b and c. And again, we can just plug in values of s. So let's plug in s equals 0. Plug in s equals 0, you're going to get 0 on the left, and on the right, you are going to get 5a. And we know that a is negative 1. So you get negative 5 plus c times 1. Okay? And so 5 is equal to c. And now what are we going to do to figure out b? We're going to plug in another value of s. Let's plug in s equals 1. Right? So you want to plug in values that will make it easy for you to figure out what the numbers are going to be. So if you plug in s equals 1, you get 2 plus 10 is 12 equals negative 1 times 1 minus 2 plus 5. That's 4. And then plus b times s, that's b, plus c, c is 5, times s plus 1, s plus 1 is 2. So 12 is equal to negative 4 plus 2b plus 10. That's 12 equals negative 4 plus 10 is 6. 6 plus 2b, subtract 6 on both sides. 6 is 2b. B is equal to 3. And that's our answer. We get that this thing, 2s squared plus 10s over s squared minus 2s plus 5 times s plus 1 is equal to negative 1 over s plus 1 plus 3s plus 5 over s squared minus 2s plus 5. Okay, so those are the examples of partial fractions. Of course, you can make them more complicated, but these are the examples, these are the basic examples we'll do. Okay. Let's just do one more. Instead of doing it all out, let's just practice setting up the forms. So for instance, if you had some polynomial over s squared plus 2s plus 5 to the third power, okay, times s minus 1 squared, what would the setup be? Well, you have this s minus 1 squared, and so that's going to be a constant over s minus 1 plus a constant over s minus 1 squared. And then you have to take care of the quadratic that's being cubed, and you're going to get cs plus d over s squared plus 2s plus 5 plus es plus f over s squared plus 2s plus 5 squared. So you have a linear factor, and you keep going until you get all the powers, plus s squared plus 2s plus 5 cubed times gs plus h. So you're going to have 1, 2, 3, 4, 5, 6, 7, 8, 8 constants that you would have to solve for in order to, that's a cubed here. You're going to have 8 constants to solve for. So it's It's messy, but this is the general form it's going to have. And this numerator has to be this P of S where the degree is less than, okay, the degree of the bottom. So it's 8, right? Degree 8. Because this S squared plus 2S plus 5, when you cube it, you're going to get S to the 6th. And then this S minus 1 squared, you're going to get S squared. And then you multiply them, you get S to the 8th. Okay, and the degree of the numerator needs to be less than the degree of the denominator in order for this to work. What happens if the degree of the numerator is bigger than the degree of the denominator? Or what if the denominator, what if the degree of the numerator is equal to the degree of the denominator? Then in that case, you can do something called long division. And when you do long division, you can write it as a polynomial plus a polynomial over your denominator, and the resulting rational function you get is going to have numerator over denominator where the degree of the numerator is less than the degree of the denominator. And then you do partial fractions to that. Yeah. We might do examples of that. This is only when the degree of the numerator is less than the degree of the denominator to do partial fractions. And then another thing is that you can't do partial fractions when your numerator is not a polynomial. So if your denominator is a polynomial, but your numerator is like, e to something, then you cannot do partial fractions to that. So that shows up sometimes when you're doing Laplace transforms in differential equations. Like you get something that's not a polynomial over a polynomial. And then one of the common mistakes is to do partial fractions. And if you think about it, if you have a setup where you have this thing on the right, okay, and then you imagine this, you multiplying it all out, you're not going to get e or sine of anything or anything like that. When you cross multiply, you distribute all of it out, you're going to get like a polynomial. So this really only works when you have a polynomial over a polynomial. And one thing I didn't go over is why do you need all these extra factors, right? That's a very good question. Like, why do you need, like in this example with a repeated linear factor, what happens if you just didn't have, this a over s minus 1? Well, you can see that you would not be able to solve for b and c. If you just didn't have the a over s minus 1, and you had b over s minus 1 squared plus c over s plus 3, and you just do the same steps, you'll see that you will not be able to solve for b and c. Basically, you will have, you're going to get 3 equations with b and c, and that's not going to have, that one is not going to have a solution. Okay? So it turns out that you really do need, in the general theory, you really do need a term for each of the powers leading up to the power that you have. Okay? Okay, so that's all I want to say about partial fractions. Thanks.